across the silent canvas of space. A new discovery has left scientists breathless. A colossal force is dragging the Milky Way at over 1.3 million miles per hour, as if our entire galaxy were nothing more than a fragile leaf caught in an invisible cosmic whirlpool. No one can see it. No one knows what it truly is. Yet the motion of thousands of galaxies reveals the footprint of a power beyond imagination. What do you think could be strong enough to pull an entire galaxy? Share your thoughts below. Your idea might open the door to a whole new perspective. And now, we step into the heart of the mystery. What is dragging the Milky Way at over 1 million miles an hour? What could possibly be pulling our entire Milky Way through the dark sea of space at 600 kilometers per second? We look up and the sky seems calm, patient, like an ancient painting that never moves. Yet the truth is far stranger. Our galaxy is not resting in the void. It is rushing through the cosmic deep with a silent urgency, as if some invisible tide were gripping every star, every planet, every dream we have ever had, and pulling them all in one direction. For a long time, we thought we understood why galaxies move. The universe is expanding, space itself stretching like the surface of a balloon as it is blown up. Draw little dots for galaxies on that balloon and they all drift apart from one another. The farther they are, the faster they recede. That simple law of expansion was the great gift of Edwin Hubble, and it seemed to tell a clear story about our place in the cosmos. But when astronomers looked more carefully at the motions of galaxies around us, they found that the story was not so simple. Some galaxies were moving away more quickly than expansion alone could explain. Some not as quickly. Some drifting slightly sideways relative to the smooth outward flow. It was as if the dots on the balloon were not just being carried by the stretching rubber, but also tugged by invisible strings tied between them. That extra motion has a quiet name: peculiar velocity. It does not mean strange in the everyday sense. It simply means motion that is not due to the general expansion of space. When astronomers compare how far away a galaxy truly is with how fast it appears to recede, they can separate the two pieces, the expansion part and the peculiar part. And when they did this for hundreds and then thousands of galaxies, a pattern emerged. Those peculiar motions were not random. Our own Milky Way, the Andromeda Galaxy, the local group and many clusters around us all shared a gentle but persistent drift in the same broad direction, as though many leaves were caught in the same slow current under the surface of a river. We are moving at roughly 600 kilometers per second relative to the background light of the universe. And that velocity has a direction. It points to a region of the sky that was for a long time one of the most stubborn blind spots in astronomy. Right where the flow seems to lead. The Milky Way itself blocks our view. The dense plane of our galaxy is filled with dust and gas, with billions of stars whose light creates a glowing fog. Invisible light. That region is almost impenetrable. Astronomers gave it a poetic and slightly frustrated name: the zone of avoidance. Not because there is nothing there, but because our eyes and our oldest telescopes could not pierce the curtain. Yet the numbers whispered that something massive must be hiding behind that curtain. Gravity does not lie. It leaves fingerprints in motion. The way galaxies around us drift. The way their peculiar velocities line up like iron filings around a magnet. All of it suggests an overdense region pulling on us from beyond the glare of our own stars. Astronomers gave that unseen mass a name even before they could map it clearly. They called it the Great Attractor. The name sounds dramatic, almost mythic, but beneath the drama lies something very simple. Somewhere out there, the universe is a little heavier than average, and gravity is doing what gravity always does. Over time, with radio telescopes, with infrared observatories, with X-ray surveys that can see the scorching gas between galaxies, astronomers began to sketch the rough outline of this hidden region. They found clusters of galaxies like the Norma cluster, filaments like the Norma wall, superclusters like Hydra and Centaurus, all woven together into a knot of structure in the cosmic web. It is tempting to imagine the Great Attractor as a single monstrous object, some titanic black hole or singular galaxy that drags everything toward it. But the truth appears to be more subtle and, in a way, more beautiful. The Great Attractor is likely not a point, but a landscape. A region where the density of matter, both visible and dark, is higher than average across hundreds of millions of light years. One astronomer once remarked that the universe is not a random scattering of islands, but a web of continents and oceans. In that sense, the Great Attractor is not a lonely mountain. It is a range, a complex of peaks and valleys shaping the flow around it. Our galaxy is not falling into a simple hole. We are gliding down a vast gravitational slope whose full shape we are only beginning to perceive. The concept of peculiar velocity may sound technical, yet it carries a quiet philosophical weight. It tells us that our motion is made of layers. One layer is the expansion that everything shares, the gentle recession written into the fabric of space from the first fire of the cosmos. Another layer is local, the mutual pulls between galaxies and clusters bound together by their own gravity. When scientists separate these layers with painstaking measurements, they are in a sense peeling back the visible universe to reveal the invisible scaffolding beneath. We cannot see dark matter directly. We cannot take a picture of gravity itself. But we can watch how galaxies respond, how they speed up, slow down, bend, and curve around concentrations of mass. That response is the language in which the cosmos tells us where its deepest structures lie. In this language, the Great Attractor is a sentence written in the motion of thousands of galaxies. Their peculiar velocities point and whisper. There is something there. You cannot see it yet, but you are part of its story. Some cosmologists remind us that what we call the Great Attractor may itself be only one act of a larger play. Beyond it lies the Shapley Supercluster, an even larger overdensity that could be contributing a major share of the pull we feel. Our region of the universe belongs to a giant supercluster called Laniakea, a name that means immense heaven. In that grand structure, flows of galaxies move along filaments, like rivers sliding down toward deeper basins of gravity. So when we ask what is pulling the Milky Way at 600 kilometers per second, there is no single simple answer. The Great Attractor is part of it. The Shapley concentration is part of it. The vast voids behind us that lack mass and therefore let us slip away more easily are part of it. Our motion is not a straight arrow. It is the result of a long conversation between matter and emptiness on scales that dwarf our imagination. One theoretical physicist once reflected that to understand our motion is to admit that we are not at rest, even in a cosmic sense. We often picture ourselves as stationary observers, watching the universe expand around us. But that picture is an illusion born of habit, not of physics. In reality, our solar system orbits the center of the Milky Way. The Milky Way moves within the local group. The local group falls toward the Virgo cluster. And all of these together flow toward the Great Attractor region and beyond. From a human perspective, our lives feel small and fixed. We have streets and houses and familiar horizons, and it is easy to believe that stillness is our natural state. Yet every moment, even as we drink tea or drift towards sleep, we are being carried through the dark at unimaginable speed by forces we cannot sense directly. That realization can be unsettling, but it can also be strangely calming. In the soft rhythm of a slow voice reading these words, you might imagine the Milky Way itself as a great luminous ship, its spiral arms like sails, billowing gently in the invisible wind of gravity. The Great Attractor is not a monster waiting to devour us, but part of the current that carries our ship through the wider ocean of Laniakea. The expansion of the universe is the tide. Gravity is the pattern of waves. We are simply a passenger, briefly awake between two eternities of darkness. From my own point of view, there is a quiet lesson in all of this. The more clearly we measure the universe, the more it teaches us humility. We discovered peculiar velocities while trying to refine our cosmic maps. And in the process we were forced to admit that vast structures influence our fate without ever appearing in our early atlases. We named the Great Attractor before we truly understood it, like children giving a title to a distant mountain whose summit they have never climbed. That is perhaps the deepest value of this story. Not only that, there is something enormous tugging on our galaxy, but that we can infer its presence at all. With faint photons gathered over decades, with careful comparisons of distance and velocity, with equations whispered across blackboards and computer screens, we have learned to sense shapes we cannot see. The universe remains full of hidden structures, yet our minds are capable of tracing their outlines in the dance of galaxies. A thoughtful cosmologist once suggested that the real map of the universe is not drawn in stars but in flows. The Great Attractor, the superclusters, the voids. They are waypoints in a grand circulation that began in the first fractions of a second after the birth of space and time. To study peculiar velocity is to listen for the echo of that beginning in the motion of the present. And for us, sitting on a small planet in an ordinary star system, there is a gentle invitation hidden here. If everything on the largest scales is in motion, if even galaxies are passengers on currents they did not choose, then perhaps our own lives are not so different. We too are shaped by forces we barely understand, drawn toward possibilities we cannot yet see. The lesson is not to fear that pull, but to remain curious about it. So when you hear that the Milky Way is racing through space at 600 kilometers per second, pulled by the mysterious mass we call the Great Attractor, you can let the numbers wash over you like a lullaby. Behind those numbers is a simple truth. We are part of a living universe, full of flows and patterns and hidden depths. We do not yet know the full shape of the current that carries us, but we are learning to read the ripples. And in that slow act of understanding, there is both science and a kind of quiet peace. What exactly is the Great Attractor? A single monstrous object or an entire ocean of gravity spread across hundreds of millions of light years? Astronomers once hoped it would be simple, that somewhere in the sky there would be a single blazing cluster or a titanic black hole that we could point to and say, "There, that is what is pulling us." Instead, they found something far more unsettling. A region so crowded with matter that space itself seems to sag in its direction. Yet most of it hides behind the bright and dusty disk of our own galaxy. To reach it with the mind, you must first imagine standing on a tiny island of stars and discovering that your whole island is drifting with a strange urgency toward a foggy shore you cannot see. When astronomers like Brent Tully and Alan Dressler measured the motions of nearby galaxies in painstaking detail, they realized that simple expansion could not explain what they were seeing. The universe was, indeed, stretching. Yet on top of that smooth outward flow, every galaxy in our local region carried an extra motion. A peculiar velocity, as if responding to a distant gravitational call. Our own Milky Way, along with the entire local group and the Virgo cluster itself, is racing through space at hundreds of kilometers per second relative to the ancient light of the cosmic microwave background. That preferred direction is the first fingerprint of the Great Attractor, a kind of cosmic tide that no one ordered yet everyone must obey. At first this was just a pattern in the numbers, a subtle tilt in the velocity field of nearby galaxies. Tully once remarked in essence that galaxies are not sitting still in the cosmic expansion but surfing on the ripples of gravity laid down by structure. Those ripples pointed stubbornly toward a patch of sky that seemed almost deliberately uncooperative, the thickest part of the Milky Way. Astronomers even gave it a slightly playful yet honest name: the zone of avoidance. Not because nothing exists there, but because our optical telescopes are nearly blind in that direction, dazzled by billions of foreground stars and choked by veils of dust. So they changed the way they listened to the universe. Instead of visible light, they turned to radio waves that pass through dust like whispers through fog, to infrared that reveals cooler stars and hidden structures, to X-rays that flare from clouds of incredibly hot gas bound inside clusters of galaxies. Slowly a new picture emerged, not of a single object but of a dense knot in the cosmic web, a confluence of clusters, walls and filaments, all overlapping in the same general region of the sky. At its heart lies the Norma cluster, a massive swarm of galaxies embedded in a halo of dark matter and X-ray glowing gas, surrounded by the long stretch of the Norma wall and neighboring structures like Hydra and Centaurus. Here the Great Attractor reveals its true character. It is not a solitary monster at the center of everything. It is a crowded intersection of the cosmic web. Netta Buckle has often emphasized that on large scales the universe is not random, but arranged into a network of clusters and filaments, with vast voids in between. The Great Attractor is simply one of the most impressive knots in that network, a place where matter has gathered more eagerly than average, and where gravity has carved a broad valley in the landscape of space-time. We feel that valley as a steady downhill pull, even though we cannot see the full depth of it with our eyes. To understand why this is so powerful, imagine again the classic analogy of dots on a balloon being carried apart as the balloon inflates. That is cosmic expansion, calm, uniform, inevitable. Now tie some of the dots together with invisible strings. Those strings are gravity. Where many strings converge in one region, the dots do not simply drift, they surge. They stream toward that area even as the balloon continues to grow. The Great Attractor is such a convergence zone, a basin in the gravitational field where the invisible strings of matter are especially tangled and tight. It does not cancel expansion, but rides on top of it, redirecting the flows of galaxies like a hidden riverbed beneath a rising tide. And still the story grows larger. In 2014, a group led by Tully proposed a new way of mapping our cosmic neighborhood using not only where galaxies are but how they move. They found that the local group, the Virgo cluster, the Great Attractor region, and many other structures are all part of one enormous supercluster that they named Laniakea, vast heaven in Hawaiian. In this view, the Great Attractor is no longer the ultimate destination. It is a bend in a much longer gravitational current that flows across some 500 million light-years, feeding into even grander concentrations of mass farther away. One of those more distant heavyweights is the Shapley Supercluster, a titanic congregation of galaxies whose combined gravity may be tugging on us even more strongly than the Great Attractor itself. Jim Peebles once pointed out that our motion through the universe is the cumulative effect of matter on many scales, not a single isolated pull. In that sense, the Great Attractor is like the first mountain range that sailors see when they approach a new continent. Impressive, dominant on the horizon, yet only part of a much larger landmass still concealed by distance and perspective. There is another actor in this quiet drama, and it is the one we never see directly. Dark matter supplies most of the mass that makes a region like the Great Attractor so compelling. The visible galaxies and hot gas are just lanterns hanging on an invisible scaffold. By reconstructing the flows of galaxies, cosmologists draw rough maps of this hidden distribution, adding depth where gravity appears strongest. Every peculiar velocity is a clue. Every deviation from smooth expansion is a fingerprint of the unseen. In this sense, the Great Attractor is not only a place but also a tool, a natural experiment that lets us test our understanding of gravity and dark matter on truly gigantic scales. Yet, even as we learn more, the mystery refuses to close neatly. Where exactly does the Great Attractor begin and end? There is no sharp edge, only a gradual fading of influence into the surrounding web. How much of the motion we observe comes from this region alone, and how much from Shapley or from other overdensities, beyond our current surveys? And what of the voids, the great underdense regions that surround these nodes of structure? Recent work speaks of a dipole repeller, a vast low-density region opposite the Great Attractor that effectively lets us slide away from it, making the pull from overdense regions even more pronounced. In the words of Yehuda Hoffman and collaborators, we are pushed by the void and pulled by the cluster. For us, tiny beings riding a star along one spiral arm of a middling galaxy, there is something deeply humbling in this realization. We are not at rest, not even drifting casually. We are being carried within layer upon layer of motion. The Earth around the Sun around the Milky Way, the Milky Way toward Virgo, Virgo toward the Great Attractor, the Great Attractor and its neighbors toward Shapley, all of it afloat in an expanding cosmos dominated by dark energy. The Great Attractor is one verse in a longer poem of movement, and by studying it, we learn to read the hidden rhythm of the universe itself. If you feel a quiet shiver when you imagine our entire galaxy being drawn through the dark toward an unseen valley of gravity, you are not alone. This channel exists precisely for that feeling, the moment when science and wonder meet in the same breath. When you tap like, when you choose to subscribe, you are not just feeding an algorithm. You are helping to weave a small human current inside this much larger cosmic flow, a community of minds drifting together toward deeper questions. And your comment, your own speculation about what the Great Attractor truly is, becomes another little star in this shared sky of curiosity. So the question remains, and perhaps it is richer now than when we began. What is the Great Attractor really? Not just in terms of mass and distance, but in what it reveals about how the universe is woven together. A single object cannot hold this role. It takes a region, a crowd, a web of matter and dark matter entwined across hundreds of millions of light years. In listening to its pull, we are also listening to the memory of the early universe, to the tiny fluctuations that grew into today's cosmic architecture. Stay with this question as we move deeper into the map of flows and voids. For the path carved by the Great Attractor may yet lead us to an even more profound understanding of where we are and what kind of universe we truly inhabit. Why would one of the most powerful gravitational engines in our cosmic neighborhood choose to remain almost completely unseen? We call it the Great Attractor, but when we point our best optical telescopes toward its direction, we find not a brilliant cluster blazing against the dark, but a thick curtain of stars and dust that swallows the light before it can ever reach us. This is the paradox at the heart of the zone of avoidance, a region of the sky where the Milky Way itself becomes a wall of fog, hiding from us whatever is shaping the motion of thousands of galaxies. To understand why the Great Attractor seems invisible, we have to imagine where it lives in our sky, not above us or below us, but straight through the glowing midplane of our own galaxy. When you look into the Milky Way on a dark night, what you see as a soft river of light is actually a swarm of hundreds of billions of suns, tangled with clouds of gas and dust so thick that visible light is scattered and absorbed before it can escape. Astronomers gave that region a quiet but telling name, the zone of avoidance, not because there is nothing behind it, but because for a long time our instruments simply could not see through it. In public lectures, researchers like Brent Tully often remind us that galaxies are not just dots on a map. They are test particles in a cosmic flow, their motions whispering the shape of invisible mass around them. When astronomers in the late 20th century measured the velocities of nearby galaxies, they realized something unsettling. Many of them were drifting in the same general direction, as though some great valley in the gravitational landscape were drawing them in. Our own local group was part of this motion, racing at hundreds of kilometers per second relative to the faint microwave afterglow of the Big Bang. Yet, when they looked for the obvious culprit in visible light, they found nothing that could explain such a pull. No single monstrous galaxy. No glaring cluster that shouted its dominance across the sky. Instead, the trail of motion led straight into that bright, crowded strip of stars that marks the heart of the Milky Way, into the zone of avoidance. It is as if you were trying to study the landscape on the far side of a blazing city at night. But every time you raise your eyes, you are blinded by the city lights in front of you. In this sense, the Great Attractor is not truly invisible. It is merely hidden behind a foreground so overwhelming that our human eyes, and the optical instruments we first built, could not separate the background from the glare. As cosmologist Netta Bakul has emphasized in many discussions, the universe is not only what we see, it is also what we are currently unable to see because of the limitations of our detectors and our vantage point. The zone of avoidance is a reminder that sometimes the greatest mysteries sit exactly behind the brightest familiar things. Dust is the quiet architect of this invisibility. Tiny grains of carbon and silicate drift between the stars of the Milky Way, each one no larger than smoke. Yet together they form a veil thick enough to choke off most visible light from beyond. Starlight scatters and reddens as it passes through these clouds, until distant galaxies vanish almost completely from our view. erased not by cosmic emptiness, but by an overabundance of matter too near and too familiar. Billions of suns in our own disk blaze like a crowded city of light, and the faint lanterns of faraway clusters are lost in the glow. But light is not a single language. It has many dialects, and while dust is ruthless to visible wavelengths, it is far more forgiving to others. Radio waves slide past dust grains almost untouched, whispering to us from the neutral hydrogen in distant galaxies. Infrared light can weave its way through the murk, revealing cooler stars and obscured structures that optical telescopes miss. And even more dramatically, X-ray emission from gas heated to tens of millions of degrees can blaze through the fog, marking the presence of massive clusters where galaxies and hot plasma are bound together by gravity. So astronomers learn to change the way they listen. Instead of staring with optical eyes into the zone of avoidance and seeing only a star-crowded blur, they began to map the region in radio, in infrared, and in X-rays. Bit by bit, the silhouette of the hidden landscape emerged. A dense cluster of galaxies known as the Norma cluster appeared as a knot of X-ray emitting gas, strongly suggesting a deep gravitational well. Long filaments of galaxies were traced across the sky, forming what we now call the Norma Wall, a kind of cosmic ridge where matter has piled up over billions of years. In interviews, astronomers often describe the process with analogies drawn from everyday life. One might say that searching for the Great Attractor is like feeling the shape of a rock beneath a blanket. You cannot see the rock directly, but the way the fabric sags and folds tells you where the mass must be. The motions of galaxies are the folds in that blanket, a subtle but undeniable pattern pointing toward the hidden overdensity. As these patterns were mapped more precisely, it became clear that the Great Attractor is not a single compact object, but a crowded region of clusters and filaments whose combined mass sculpts the local flow of galaxies. The invisibility, then, is not absolute. It is conditional. To our naked eyes, the Great Attractor does not appear because we are tuned to the wrong part of the spectrum and trapped behind the wrong foreground. To our instruments that can see radio and infrared and X-ray light, the region becomes more legible, though still incomplete. And even beyond that, there remains an unseen component that no form of light can reveal directly: the dark matter that pervades these structures. Physicist Vera Rubin spent her career showing that galaxies rotate too fast for their visible mass alone to hold them together, compelling us to accept that most of the mass in the universe is dark. The Great Attractor is another echo of that lesson. The gravitational pull we infer from the flow of galaxies is stronger than what luminous matter alone can explain. So even when we peer through the zone of avoidance with every wavelength available, we still know that a large fraction of the region remains invisible in a deeper sense, not because of dust, but because of the fundamental nature of the matter itself. There is a quiet humility in this realization. Our galaxy, which once felt like the grand stage of the cosmos, is revealed as just another actor being pulled along by currents it cannot see. In a way, the Great Attractor is less a single destination and more a slope in the fabric of space-time, a direction in which the local universe leans. And we, along with millions of other suns and worlds, are simply sliding along that slope, carried by the geometry carved out by visible and invisible matter together. When we talk about these things in the calm of the night, with a gentle voice and slow breath, it becomes almost meditative, to imagine that even now, as you listen, the entire Milky Way is drifting through space, drawn toward a hidden concentration of mass, veiled by our own galactic disk. The zone of avoidance is no longer just a technical term on a sky map. It is a symbol of all the places in our understanding where familiar light is not enough, where we must learn to see differently. If this slow journey into the dark parts of the cosmos brings you a sense of wonder, or a gentle calm as you drift toward sleep, you can help these stories continue by simply tapping like, subscribing, and leaving a few thoughts of your own below. In the same way that the motion of galaxies reveals the hidden mass of the universe, your small actions reveal to the algorithm that there is value in quiet, thoughtful explorations of the night sky. Because in the end, the question of why the Great Attractor is invisible is really a question about how we look at reality. We learn that what appears bright and close can actually conceal deeper structures behind it. That what is hidden today may become visible tomorrow when we build new ways of seeing. And as our instruments improve, as new surveys peel back the zone of avoidance in ever more detail, we may find that the Great Attractor itself is only one chapter in a larger story of flows and superclusters stretching far beyond our current horizon. Until then, we float inside the Milky Way like travelers in a ship whose windows look out onto a fog-bound sea, feeling the pull of unseen currents, listening to the faint messages carried by radio waves and X-rays from beyond the dust. The universe remains partly veiled, and perhaps that is a gift, because it means there are still mysteries waiting for those who are willing to sit quietly, breathe slowly, and look again into the places we once called zones to avoid. What if the true heart of the Great Attractor is not an invisible ghost spread across the sky, but a single blazing city of galaxies called the Norma Cluster? Astronomers have followed the motion of our own galaxy like detectives watching a ship pulled by hidden tides. They found that the Milky Way is not drifting gently with the expansion of the universe. It is racing in a particular direction at hundreds of kilometers every second, more than 1 million miles every hour. That strange motion points toward a region buried behind the thickest part of our galaxy, a place where ordinary telescopes go blind. For a long time it was only a rumor in the data, a gravitational whisper. They called it the Great Attractor. Hidden within that fog of stars and dust lies the Norma Cluster, one of the most massive clusters of galaxies in our cosmic neighborhood. When radio telescopes and X-ray observatories finally pierced the veil, they did not find a single monster galaxy, but a whole metropolis of galaxies packed into a volume of space so dense that gravity there is like a deep well in the fabric of the universe. Hot gas between those galaxies glows fiercely in X-rays, reaching tens of millions of degrees. To hold such gas in place, the cluster must contain enormous amounts of dark matter, far more than what we see in stars. One cosmologist once remarked that clusters like Norma are where the skeleton of the universe shows through, because dark matter reveals itself in the way everything falls toward it. If you imagine space as an endless landscape, then the Norma Cluster is not a small hill. It is a mountain range. Galaxies roll down its slopes the way rivers follow gravity on Earth. Our local group, the Milky Way and Andromeda with their retinues of smaller companions, is like a caravan that happens to be traveling along one of those valleys. We do not see the mountain directly, but our path curves in response to its pull. Brent Tully, who spent decades mapping these flows, once said that the motions of galaxies are like arrows drawn on the sky. If you follow them long enough, They all seem to point toward the same hidden mass. Norma is special because it sits almost exactly where the data first hinted at the Great Attractor. In X-ray images, it is a blazing knot, surrounded by fainter filaments of galaxies that stretch out like the roots of a cosmic tree. Those filaments feed the cluster with fresh material, and they also guide distant galaxies along gravitational highways that converge near Norma. To many researchers, it is natural to ask whether this is the beating heart of the entire region, the central weight that shapes the flow of hundreds of millions of light-years around it. As one astronomer put it, the universe is not a random scatter of islands. It is a web, and Norma sits at one of its major intersections. Yet the story is more delicate than a single center. Gravity rarely grants us such simplicity. The Great Attractor appears to be a broad basin in the cosmic landscape, not a single point. Norma contributes a huge portion of that pull, but it shares the role with neighboring structures, other clusters and walls of galaxies that blend together in a tangled gravitational field. Some researchers emphasize that when we map the flow of galaxies, the lines do not converge on a dot. They slow and swirl through a whole region. In that sense, Norma may be less a solitary heart and more a central chamber in a larger organism. Still, when you look closely, the cluster has a personality that invites metaphor. Picture thousands of galaxies, each with billions of stars, locked together in a gravitational dance. Between them, hot gas forms a glowing atmosphere. Dark matter halos overlap and merge, creating an invisible scaffold. The cluster slowly grows as smaller groups fall into it, their galaxies stretched and stirred like streams feeding a vast sea. A theorist once mused that clusters do not simply sit in space. They are still forming right now. And by watching them, we watch gravity write history in slow motion. Norma is one chapter of that history, written deep inside the Great Attractor region. From a more human perspective, there is something humbling in the idea that our own galaxy is moving under the influence of a place we cannot see directly. We like to imagine our sky as stable, our constellations eternal. Yet all the while, the Milky Way is rushing through space, guided by invisible structures like Norma. One cosmologist commented that the cosmic microwave background, the faint afterglow of the Big Bang, is like the still surface of a pond, and our motion through it betrays the presence of distant masses, a subtle ripple in an otherwise calm reflection. That motion tells us we are not at rest, not central, but part of a much larger flow. This is where science begins to feel almost meditative. To think about the Norma cluster is to slow down inside our own thoughts, even as we acknowledge that physically we are moving at unimaginable speed. In the darkness behind the Milky Way, a hidden city of galaxies exerts its pull, and we respond without choice. Our telescopes patiently gather X-rays and radio waves, and from those faint signals we rebuild an image of a place we will never visit. The act itself is a kind of quiet devotion, a willingness to sit with the unknown and let the data slowly speak. As Alan Dressler once reflected about cluster studies, when you measure how galaxies move, you are listening to the language of gravity. In that language, Norma says that dark matter is real and abundant. The brightness of its X-ray gas would not be possible without an enormous gravitational well to hold it in place. Ordinary matter alone cannot explain it. The mass we can account for in stars and gas is only a small fraction of what is needed. The rest must be something else. In many ways, clusters are the best laboratories for testing our ideas about dark matter, and Norma is among the clearest cases. One researcher remarked that without dark matter, clusters like Norma would simply fly apart, their galaxies escaping into intergalactic space. The fact that they remain bound tells us there is more gravity there than light can show. At the same time, the role of Norma inside the Great Attractor connects to an even larger structure, the Laniakea Supercluster. When Tully and colleagues mapped the flows of thousands of galaxies, they found that our local group, the Virgo cluster, the Great Attractor region and many others are all part of one vast basin of attraction. They gave it a name meaning immense heaven. In that picture, Norma is not isolated. It is one of the deepest pockets within a gigantic gravitational valley. To ask whether Norma is the heart of the Great Attractor is also to ask how many hearts a living system can have. Whether a supercluster is a single organism or a collection of organs that share the same blood flow. And still, the mystery is not finished. Beyond Norma and the Great Attractor lies the Shapley Supercluster, a still larger concentration of galaxies that may tug on us even more strongly. Some studies suggest that a significant fraction of our motion comes from this distant giant, while another part arises from the underdense voids that seem to push us away by their very emptiness. Yehuda Hoffman once described this situation by saying that we are not simply falling toward one attractor. We are being sculpted by a whole landscape of overdensities and voids. In that landscape, Norma remains a crucial landmark, a massive peak close enough to shape our path in a tangible way. When we create a video or a story about such places, we are not only passing along facts. We are inviting people to feel the scale of what surrounds them, to sense that even their quiet nights under familiar stars are part of an immense and dynamic universe. If you find yourself drawn to that feeling, to the image of our galaxy being gently but irresistibly pulled toward a hidden cluster behind the Milky Way, you can help keep these journeys going by tapping like and subscribing, so that more travelers can join us on this slow drift through the cosmos. Each interaction is a small signal, like a photon in a detector, but together they build up a clear picture that says these stories matter. In the end, whether Norma is the single heart of the Great Attractor or one powerful chamber in a broader system may matter less than the perspective it gives us. It reminds us that our galaxy is not an island. It is part of a current. Our lives unfold inside a star that orbits a center that orbits another center that is in turn moving toward clusters like Norma, all nested within flows we barely comprehend. To sit with that knowledge is to practice a kind of cosmic contemplation, an acceptance that we are both very small and deeply connected to structures of staggering size. Somewhere behind the river of stars we see every night, the Norma cluster pulls patiently, and we answer without ever feeling the tug directly. Thought for 21 seconds. How far does the Norma wall really stretch? And could it be the secret gravity wall guiding our entire galaxy through the dark? When astronomers speak of the cosmic web, they often sound less like engineers of data and more like poets of structure. They describe filaments and voids, rivers of galaxies and deserts of nothing. Somewhere within that invisible architecture lies the Norma wall, a vast filament of matter that may span hundreds of millions of light years, a wall we cannot see with our eyes, yet one whose pull we can feel through the motion of galaxies themselves. Imagine floating inside an ocean whose currents you can feel but whose shores you can never quite see. That is our situation in the local universe. Our Milky Way drifts not in a random direction, but along a preferred path, sliding through space at hundreds of kilometers per second relative to the cosmic microwave background. For decades, this motion was a puzzle. The smooth expansion of space could not explain it. Something else was tugging on us. When researchers mapped the skies in radio waves, X-rays, and infrared light, they began to glimpse massive structures hidden behind the dense plane of the Milky Way. Among them was a crowded region of clusters and superclusters that came to be called the Great Attractor. Within that gravitational basin, one feature stood out in simulations and reconstructions of the mass distribution. A long, overdense ridge later identified as the Norma Wall. Not a brick wall, of course, but a colossal sheet of galaxies and dark matter, like the backbone of a continent whose coastline we are still tracing. To understand why such a wall matters, we have to remember that gravity is patient, relentless, and cumulative. Over billions of years, even a tiny excess of mass in one direction will slowly redirect the paths of galaxies, like a faint slope that eventually sends all the rainwater of a landscape toward one valley. The Norma Wall appears to be one of those slopes, a region where matter is just dense enough to curve the trajectories of the galaxies around it. Our own Milky Way, together with the Andromeda Galaxy and the rest of the local group, seems to be drifting along this gravitational hillside. In the language of modern cosmology, the Norma Wall is part filament, part wall, a bridge of matter connecting the great structures of the local universe. It appears alongside the Norma Cluster, a rich cluster of galaxies whose hot gas glows in X-rays, and near the Hydra and Centaurus superclusters. Together, they weave a tapestry of mass that becomes the skeletal framework of the Great Attractor region. One astronomer once compared these filaments to the steel beams inside a skyscraper, unseen from the street, yet entirely responsible for the building standing at all. The Norma Wall is one of those beams. Only here, the skyscraper is a chunk of the universe, hundreds of millions of light years across. Carl Sagan liked to say that we are a way for the cosmos to know itself. In the context of the Norma Wall, that line takes on a new shade of meaning. We are not just observers looking outward. We are passengers embedded in a moving train of galaxies, trying to measure the tracks beneath our feet while the train is still in motion. Every redshift we record, every distance we estimate, is an attempt to reconstruct this hidden railway, to see the wall that shapes our path. As one cosmologist put it in a lecture, we are mapping an invisible landscape by watching how its shadows make us move. Norma Wall is not alone. It lives inside an even larger pattern called Laniakea, the supercluster that includes the Milky Way, the Virgo cluster, and the whole Great Attractor region. When scientists first revealed Laniakea, they did it not by taking a single photograph, but by charting the motions of thousands of galaxies and tracing their flow lines backward. Those lines converged toward dense regions and bent around emptier ones, outlining a basin of attraction that they named our home supercluster. The Norma Wall appears there as a ridge within the basin, one of the main ridgelines along which galaxies slide toward deeper valleys of gravity. In this picture, the universe is not a random cloud of galaxies scattered like dust. It is more like a frozen snapshot of waves, crests and troughs of density that emerged from the early universe, and have since been amplified by gravity. Filaments like the normal wall are the crests, the places where small initial ripples became vast chains of galaxies, while cosmic voids are the troughs. The contrast between them grows over time, like mountains rising while nearby basins sink. Our Milky Way is not perched on a mountain peak, but it is clearly flowing down one side of this relief map, sliding along the normal wall toward deeper attractors beyond. Dark matter plays a central role in this story. The luminous galaxies that we see in the normal wall are like lanterns marking only a fraction of its true mass. Most of the matter there is invisible, interacting only through gravity. Nima Arkani Hamed once famously declared that space-time is doomed, a provocative way of saying that our classical picture of space and time is incomplete. Structures like the normal wall remind us of this. They are shaped by a substance we cannot yet detect directly, emerging from physics we do not fully understand, and yet their influence on our motion is undeniable. From a more meditative perspective, there is something deeply humbling in the idea that an unseen wall is guiding our entire galaxy. We live our lives under city lights, measure days in traffic and evenings by the blue glow of screens. Meanwhile, far beyond our atmosphere, far beyond even the halo of our galaxy, immense rivers of matter are flowing silently along paths set billions of years ago. The normal wall is one of those paths, a structure so vast that it dwarfs all human history, yet so gentle in its pull that it takes eons to change our trajectory by even a small fraction of the sky. Think of the Milky Way as a small boat on a very slow-moving river. To the sailors on deck, the water seems almost still, the nearby shoreline barely changing from year to year. But if you watched that boat for millions of years, you would see that the current is carrying it along a grand curve, past unseen headlands and through wide bends in the river valley. The normal wall is part of that valley, shaping the course even when the current is too gentle to feel in a human lifetime. For observers on Earth, this gentle current becomes a set of precise numbers, peculiar velocities, flow fields, reconstructed density maps. Yet behind the mathematics there is always the same basic question: where are we going? And why? The Great Attractor was the first name we gave to this mystery, a kind of placeholder that said more about our ignorance than our knowledge. As data improved, the picture became richer, revealing the Shapley concentration beyond, the broader Laniakea basin, and, woven through it all, the subtle spine of the normal wall. In many ways, the normal wall teaches us about perspective. From a narrow view, it might look like a single structure pulling us in a specific direction. From a wider view, it becomes one feature among many in a complex landscape of pushes and pulls. Widen the view further, and even Laniakea itself may turn out to be just one eddy in a grander flow extending beyond 1 billion light-years. Each time we zoom out, the wall that once seemed ultimate becomes merely local. There is a quiet philosophy hidden in that realization. We often imagine our lives, our civilizations, even our galaxy, as if they were central. But the normal wall whispers a different story, a story in which everything is part of a pattern too large to see all at once. The flows of galaxies are not random, yet they are not designed for us either. They are the natural consequence of small fluctuations in the early universe, amplified by gravity into the filaments and walls we now struggle to map. We are latecomers, waking up in a room whose architecture was laid out long before we arrived. Still, there is comfort in knowing that we can at least trace the outlines of that room. Each new survey that peers through the dust of the Milky Way, each catalogue of hidden galaxies, adds another brushstroke to the portrait of the normal wall. The image is incomplete, and perhaps it always will be. Yet with every improvement, the flow lines of our local universe become a little clearer, the slope we slide down a little better understood. In the end, the normal wall is both a scientific object and a kind of cosmic metaphor. It reminds us that the strongest influences in our lives are often invisible, felt only through their effects on our path. Just as galaxies reveal the hidden mass of the wall by the way they drift, we reveal the hidden structures of our own universe by the choices we make, the directions we are gently pulled toward. Somewhere between data and wonder, between equations and quiet night skies, the normal wall stands as a silent teacher. As you listen to these motions and imagine that vast gravitational shoreline stretching far beyond our sight, you might feel a strange calm. Our galaxy is moving, yes, but it is not lost. It follows a path written into the fabric of the cosmos long ago, flowing along the normal wall and past the Great Attractor toward destinations we can only begin to imagine. And in tracing that journey with patient measurements and quiet awe, we are doing exactly what a thinking piece of the universe is meant to do, learning how the invisible shapes the road beneath our feet. What if the missing piece of the Great Attractor mystery has been hiding in plain sight, woven into the dense heart of the Hydra Centaurus supercluster? Astronomers have long known that the galaxies around us do not simply drift with the gentle breathing of cosmic expansion. They move with a strange urgency, an added motion that refuses to follow the quiet logic of the expanding universe. This peculiar velocity has always been a whisper from something unseen, a gravitational tide deeper than the equations first suggested. And in that tide, Hydra Centaurus begins to rise like a shadowed continent beneath the cosmic sea. When the earliest flow maps were drawn in the 1970 seconds and 1980 seconds, astronomers were startled to find that countless galaxies appeared to be moving toward a region hidden behind the plane of the Milky Way. They named it the Great Attractor, a placeholder more than a solution. Brent Tully once described galaxies as test particles drifting along the invisible river of gravity. And that river, once traced carefully, bends toward Hydra Centaurus in ways few expected. Hydra Centaurus supercluster is not a single object, but a gathering of clusters, filaments, and vast walls of galaxies. Its density rises above the cosmic average like a mountain range breaking through the surface of a foggy world. Stars, hot gas, dust, and especially dark matter converge there, forming a structure whose gravitational pull can be felt across hundreds of millions of light-years. Astrophysicist Netta Barkal once said, "The largest structures shape the skeleton of the cosmos, and Hydra Centaurus may be one of those central bones." X-ray surveys reveal plasma heated to tens of millions of degrees within the region, a ghostly glow only possible if an immense gravitational well is holding the material in place. Without such gravity, that gas would have drifted away long ago. What we see is only the surface. What we do not see, the dark matter scaffolding, is likely far more massive. Every newly resolved filament around Hydra Centaurus suggests that our earlier models of the Great Attractor were too simple, too small. To a scientist, Hydra Centaurus feels less like a point and more like a bend in a river, a gravitational current guiding the motion of entire clusters. Laniakea Supercluster. The vast structure of more than 1,000,000 galaxies that includes our own is the river system. Hydra Centaurus is one of its great ridges, shaping the flow. Astronomer Hélène Courtois once described Laniakea as a drifting continent of galaxies floating on an ocean of dark matter, and Hydra Centaurus becomes a mountain range rising from that drifting land. Simulations of the peculiar motions of galaxies show that Hydra Centaurus accounts for a significant portion of our local motion, adding its pull to the influence of the Norma cluster, the Norma wall, and the other structures long attributed solely to the Great Attractor. Gravity rarely works alone. It is a choir of forces, not a single voice. Hydra Centaurus sings one of the deeper notes. There is a poetic truth in how these discoveries unfold. For decades, the Great Attractor was treated as a single destination. But the universe resists being simplified. Every new telescope, every new wavelength, uncovers another layer. The zone of avoidance once hid vast stretches of sky behind the Milky Way's dust. But radio, infrared, and especially X-ray observations pierced the veil, revealing galaxies that had been invisible for generations. Hydra Centaurus emerged gradually, not as a revelation, but as a rising coastline in the fog. The story of Hydra Centaurus is also a story of how science corrects its own myths. At first, Great Attractor seemed to be the central actor. Then the Shapley Supercluster appeared farther beyond, too massive to ignore. Hydra Centaurus took shape in between, not replacing anything, but completing the picture. As Nobel laureate Jim Peebles once remarked, the universe is a simple idea written in extremely complicated data. Hydra Centaurus is part of that complication. Beyond the technical detail, there is an emotional layer to this discovery. Imagine sitting on a small blue planet, orbiting an ordinary star, while your entire galaxy is being drawn toward a supercluster hundreds of millions of light-years away. Milky Way becomes a ship drifting on a quiet, invisible tide. Hydra Centaurus shapes that tide. It humbles us, reminding us that the forces ruling our cosmic home come from realms far beyond anything we can touch. When we say Hydra Centaurus was a missing piece, it is not an accusation. It is a reflection of how discovery works, how each generation of instruments lifts another corner of the cosmic veil. We did not overlook it. We simply could not see it yet. And, even now, we are only seeing the faint edges. The deeper flow of Laniakea shows that galaxies follow gravitational slopes like rivers follow valleys. Hydra Centaurus is one such valley, a depression in the gravitational landscape that guides part of our motion. Without it, the trajectory of the Milky Way through the cosmic web would be different. Changing its mass would be like moving mountains on a continent. The rivers would bend, the currents would shift. This idea settles slowly in the mind, like starlight reaching a telescope after a long journey. Hydra Centaurus is not a final answer, but a doorway to deeper questions. If this supercluster shapes our local flow, what lies beyond shaping Hydra Centaurus itself? Is Shapley the next ridge? The next peak? Or is there something even larger? An unseen continent of mass waiting to be uncovered in the distant dark? Meanwhile, the Milky Way drifts on, guided by Hydra Centaurus, influenced by Great Attractor, pulled farther toward Shapley. This flow will continue for longer than any civilization will ever last. When we close our eyes, listening to the quiet hum of the cosmic story, perhaps the most beautiful gift Hydra Centaurus offers is not an explanation, but a feeling that we are passengers on a vast, gentle current, moving through a universe that is larger, deeper, and more mysterious than we can ever fully imagine. And each missing piece we finally find makes the cosmic tapestry both clearer and more wondrous. What if the true puppet master of our motion through the cosmos is not the Great Attractor at all, but a far more distant giant known as the Shapley Supercluster? For decades we have spoken about the Great Attractor as if it were the main character in this quiet drama of drifting galaxies. We imagine a hidden mass tugging on the Milky Way, urging our entire local group to fall toward one region of the sky at hundreds of kilometers per second. Yet when astronomers widened the map and traced the flow of galaxies over hundreds of millions of light years, a new figure stepped forward from the darkness. Larger, heavier, more remote. The Shapley Supercluster began to look less like a background extra and more like the unseen hand shaping the stage itself. The Shapley Supercluster is not a single cluster of galaxies, but a vast congregation of clusters bound together by gravity. It occupies a region of space so rich in mass that some astronomers describe it as one of the densest concentrations of galaxies in the nearby universe. While the Great Attractor region already contains enormous structures like the Norma Cluster and Hydra Centaurus, Shapley may outweigh it by a factor of several times. In simple language, it is like discovering that the hill you thought was pulling the river is actually just a slope on the flank of a distant mountain range. The water flows not because of the little hill alone, but because of the faraway massif that bends the landscape on a grander scale. When researchers such as Brent Tully and his collaborators mapped the motions of galaxies in 3 dimensions, they noticed something striking. The flow of matter in our region of the universe does not simply converge on the Great Attractor and stop there. Instead, the stream keeps going, as if the Great Attractor were just a bend in a much longer river. Far beyond it, in the direction of the constellation Centaurus, lies Shapley, a gargantuan assembly of clusters whose collective gravity appears to pull not just us, but entire swaths of the cosmic web. One cosmologist remarked that Shapley is like a giant weight sewn into one side of the fabric of space, subtly distorting everything around it. To feel the scale of this, imagine a night sky where every star you see is replaced by a galaxy. Then pack tens of thousands of those galaxies into a single region, surrounded by many more just beyond. The Shapley Supercluster resides roughly 600 million light-years away, yet its gravity whispers across that gulf. It does not yell. It does not tug like a violent storm. It is more like a deep, patient tide, guiding the drift of galaxy clusters over hundreds of millions of years. As astrophysicist Netta Bakal once said about these massive structures, they are the great cities of the universe, surrounded by sprawling suburbs of galaxies that slowly fall inward over cosmic time. The question then becomes, if Shapley is so powerful, how much of our own peculiar velocity can it explain? The Great Attractor accounts for a noticeable part of the motion we see in the cosmic microwave background dipole. That slight hot and cold asymmetry that tells us we are moving with respect to the primordial light of the Big Bang. But detailed reconstructions of the velocity field suggest that the pull from the Great Attractor alone is not enough. The numbers simply do not close. There is a missing contribution. When Shapley is added to the model, a large fraction of that missing motion falls into place. Suddenly, the flow of galaxies looks less chaotic and more like a continuous descent down a long gravitational slope that stretches from our local group all the way towards Shapley. Some researchers describe this using a simple image: a marble rolling on a warped sheet. The Great Attractor is a noticeable dip nearby, but the sheet itself is gently tilted by the far deeper hollow where Shapley lies. Our marble does roll toward the local dip, yet its overall journey is guided by the distant basin. In this picture, the Great Attractor is not a final destination. It is a contour on the way downhill. The Shapley Supercluster shapes the tilt of the entire landscape, and we and our neighboring galaxies simply obey that geometry. As cosmologist George Efstathiou once noted in a different context, the universe on large scales is less like a random scattering of islands and more like an intricate network of valleys and ridges in which galaxies flow along predetermined paths. There is a quiet, humbling beauty in this realization. We tend to imagine our galaxy as a sort of anchor point, a place around which we measure everything else. But on the scale of Shapley, the Milky Way is a grain of dust being carried on a breeze it will never feel directly. Our stars, our planets, our histories and dreams, all participate in a slow-motion dance choreographed by gravity emanating from a realm so distant that no human eye will ever see it without instruments. This is the sense in which astrophysicist Subramanian Chandrasekhar once spoke of astronomy as a search for a sense of proportion, a practice that constantly resets our understanding of what is large and what is small. Of course, the story is not finished. When scientists talk about the Shapley Supercluster as a possible main driver of our motion, they do so with caution. The maps of galaxy distances are incomplete. The distribution of dark matter is still inferred rather than directly seen. And the influence of cosmic voids such as the so-called dipole repeller also enters the picture. Yehuda Hoffman and his colleagues have shown that our local group may be simultaneously pulled by dense regions like Shapley and pushed away by enormous underdense regions, creating a kind of gravitational push-pull that shapes the full pattern of our motion. In their words, voids are not empty gaps, but active sculptors of the cosmic web. In this delicate interplay, Shapley stands out as one of the heaviest nodes in the network. Its very presence forces us to rethink simple narratives where a single great attractor sits like a cosmic drain and everything swirls into it. Instead, we see a universe where many attractors share the stage, where mass is concentrated along filaments that feed into one another, and where our own trajectory is the result of countless influences integrated over billions of years. The Shapley Supercluster becomes not a villain or a hero, but a colossal landmark in a landscape of gravity that we are only beginning to chart. If you listen carefully to the tone of modern cosmology, you hear this blend of precision and awe. On the one hand, researchers construct velocity fields, apply Bayesian reconstructions, and feed supercomputers with data from redshift surveys. On the other hand, many of them speak of these structures in almost poetic terms. Brent Tully has compared our supercluster home Laniakea to an enormous basin of attraction, a region where the flow lines of galaxies converge like rivers to the sea. Shapley, sitting out near the rim of that basin, may be one of the deepest points in this cosmic seabed. For a listener settling into the dark with headphones on, trying to drift towards sleep while learning about the universe, there is something meditative in imagining this. You can picture the Milky Way as a small luminous boat, floating on a slow current that you cannot feel from the deck. The night sky above seems still, the constellations unmoving. Yet beneath this apparent calm, the entire river of galaxies is sliding ever so gently down a slope determined by far-off mass concentrations like the Shapley Supercluster. Nothing about your life changes from one second to the next. But across hundreds of millions of years, our galaxy will have drifted a significant distance along that invisible gradient. Some philosophers of science have noted that discoveries like this subtly change the way we think about destiny, not in a mystical sense, but in a physical one. Our cosmic neighborhood is not random, it is structured. Our motion is not arbitrary. It is guided by the distribution of mass on scales far beyond our direct experience. As physicist John Wheeler once wrote, "Mass tells space-time how to curve, and space-time tells mass how to move." The Shapley Supercluster is a towering example of that principle made manifest across 500 million light-years. It curves the fabric, and in response, we move. In the end, whether Shapley is truly the main architect of our peculiar velocity or simply one of several major contributors, it already serves a powerful role in our imagination. It reminds us that what feels local is often controlled by what is distant, that the quiet arc of the Milky Way across the sky is part of a vaster choreography unfolding on scales we can barely grasp. To ask whether the Shapley Supercluster is the one behind it, all is to open a door into this larger way of seeing. We may never stand outside the universe to watch the whole cosmic web at once, but through structures like Shapley, we catch a glimpse of the grand design of motion and mass. And as we drift along that almost imperceptible current, we carry with us the quiet understanding that even in our smallness, we are participants in a story written across hundreds of millions of light years. What if the Great Attractor were only a tiny corner of a far greater map that quietly guides our galaxy through the dark? Astronomers once thought they were chasing a single mysterious center of pull, a heavy knot in space called the Great Attractor, something that seemed to tug on the Milky Way and thousands of neighboring galaxies all at once. But as they traced the motion of these galaxies more carefully, they began to notice that the flow did not stop there. It curved and stretched far beyond that bright gravitational hotspot, as if the current of space itself were part of a much larger ocean. Out of this realization was born a new name that is quietly changing how we see our home in the universe: the Laniakea Supercluster. Laniakea means vast heaven or immeasurable skies in Hawaiian, a poetic choice for a structure so immense that it holds more than 100,000 galaxies in its invisible embrace. Inside this region live the Milky Way, the familiar Virgo cluster, the Great Attractor, and many other walls and filaments of galaxies we are only beginning to chart. Cosmologist Brent Tully, one of the scientists who helped define Laniakea, once said that we needed a way to name our cosmic address, beyond just Milky Way or local group, that only by seeing the full pattern of motions could we recognize the continent of gravity we inhabit. It is as if we had been living in a single valley all along, and only recently climbed high enough to see that the valley lies on the slope of a much larger mountain range. The key to this discovery is the idea of a gravitational flow, a cosmic river of motion. Galaxies are not simply frozen dots painted on an expanding balloon. They drift and slide along the curves of the cosmic web, pulled toward regions where matter is dense and quietly released from vast empty voids behind them. When astronomers measured not just where galaxies are, but how they are moving relative to the smooth expansion of the universe, they saw something striking. Streams of galaxies appeared to converge toward a broad basin in space, while at the same time flowing away from an immense underdense region on the opposite side. The Great Attractor was only a bend in that river, not the source of the current itself. Shapley Supercluster is defined not so much by a sharp border as by this pattern of motion. If a galaxy is falling inward toward the same gravitational basin as we are, it belongs to Shapley. If its path bends away toward some other distant attractor, it belongs to another supercluster. In this sense, the map of Shapley is more like a map of ocean currents than a map of continents. It shows where the flows gather and where they part, where gravity carves valleys in the fabric of space-time, and where emptiness allows galaxies to drift away like foam on deep water. Astrophysicist Hélène Courtois has described this idea as listening to the music of cosmic motion rather than just staring at a static picture. The dance reveals the structure that the snapshot hides. For our own galaxy, this picture is quietly humbling. We like to imagine the Milky Way as a great island of stars sailing through nothingness, sovereign and alone. In truth, we are more like a small boat caught in a vast and gentle tide, moving at hundreds of kilometers each second toward the center of this gravitational basin. The Virgo cluster ahead of us, the Great Attractor beyond it, and still, farther concentrations of matter like the Shapley Supercluster all shape the slope down which we glide. Behind us, a giant cosmic void contributes its own strange influence by simply not being there, its lack of matter leaving nothing to hold us back. As cosmologist Netta Barkall has often reminded students, the universe is not only made of things, it is also sculpted by the absence of things. In this meditative view, Shapley becomes less a cold catalogue entry and more a landscape of belonging. We find ourselves at the edge of a luminous stream, our galaxy one bright droplet among many, its motion part of a slow, grand circulation that has been unfolding for billions of years. When you hear the phrase Shapley Supercluster, you can imagine not just a cluster of clusters, but a region of the universe where many stories of light are being braided together by gravity into a single larger narrative. The Milky Way and Andromeda, the giant ellipticals of Virgo, the hidden galaxies behind the plane of our own system, all of them are travelers in the same basin of attraction. This larger context also reshapes how we think about the Great Attractor itself. At first it seemed like a cosmic monster, a singular destination pulling everything into its maw. Now it appears more like a whirlpool along a broader current, strong and impressive, yet still part of a larger pattern woven by Shapley. The question then shifts from what is the Great Attractor to how does this basin of gravity form and evolve over time. It pushes us to ask how dark matter is arranged on these tremendous scales, how ancient density ripples from the early universe have grown into the filaments and knots we see today. As theoretical physicist Jim Peebles likes to say, the large-scale structure of the universe is a fossil record of its youth, written not in rock but in the distribution of galaxies themselves. When you picture Shapley, You might imagine tracing threads of light through a deep, immersive night. Each thread is a filament of galaxies, each knot a cluster, each faint offshoot a lonely group like our own. Gravity pulls along these threads. Matter flows where other matter has already gathered, and the dark matter skeleton beneath it all channels the motion in ways we cannot see directly but can infer from the dance of the galaxies. Observational cosmographer Yehuda Hoffman once compared these flows to wind patterns around mountains. You may not see the air itself, but the way clouds move tells you where the peaks and valleys lie. There is also a quiet philosophical echo hidden here. For centuries, humans looked up at the sky and saw fixed constellations, a timeless dome of stars. Then we learned that the stars move, that the Milky Way rotates, that galaxies collide. Now Laniakea reminds us that even the patterns we once thought were final are themselves drifting inside something larger. Our so-called local universe is not a static frame. It is a flowing part of a still greater sea. Astrophysicist Neil deGrasse Tyson often notes that we are not only in the universe is in us. But here we might add that we are also in a current, carried along by structures too vast to ever cross in a lifetime. In the gentle pace of a late-night listening session, this realization can feel strangely soothing. The same forces that guide the Virgo cluster and the Great Attractor are guiding us as well, whether we are aware of them or not. Instead of imagining ourselves lost in randomness, we can think of our galaxy as belonging to a larger family, sharing a common fate within the Laniakea Supercluster. Our future mergers, our eventual isolation as dark energy stretches distant galaxies away, our long spiral around the basin of gravity, all of it is part of this quiet choreography. So when you hear that, the Great Attractor may be only a small corner of something vaster, you can let that thought unfold slowly in your mind like a distant sunrise over an unknown shore. Laniakea is that shore, a name we give to the immense region whose pull we feel but whose full outline we may never see with human eyes. To study it is to read the currents that move us, to trace the story of how matter and gravity have shaped not just our sky, but our very sense of place in the cosmos. And somewhere deep in that awareness, between wakefulness and sleep, there is a simple question that keeps returning like a tide. If our entire galaxy is just one traveler in the river of Laniakea, what greater journeys might the universe itself be taking beyond the horizons we can ever know? Can the universe itself push entire galaxies away from it? We are used to thinking of gravity as a hand that only pulls, a quiet invitation downward and inward. But in the deep maps of cosmic motion there is a strange pattern that feels almost like a breath in reverse. Behind our local group of galaxies, behind the Milky Way and Andromeda and the faint companions that circle us like fireflies around a lantern, there stretches a vast, underdense region, a cosmic hollow that astronomers have come to call the dipole repeller, a place not of force but of absence. It is not a monster made of dark energy, not some new anti-gravity field pushing everything away. It is simply a region where there is less stuff than average, less matter to tug and hold and slow. And yet, when we trace the motion of galaxies through space, when we follow their peculiar velocities on top of the general expansion of the universe, we see a pattern that is impossible to ignore. Our whole neighborhood is flowing, like a river of light sliding between two shores, toward overdense regions such as the Great Attractor and the Shapley Supercluster, and away from this enormous void behind us. as cosmologists studying large-scale flows have pointed out. Voids can steer galaxies just as powerfully as clusters do, not by pushing but by failing to pull. In their reconstructions of the cosmic velocity field, researchers like Yehuda, Hoffman and Brent Tully have shown that when you remove matter from a region, you create an imbalance, a gentle downhill slope in the fabric of gravity itself. Imagine standing between a mountain range and an open ocean of mist. The mountains behind you are gone, eroded away by time, and in front of you a distant ridge still rises, faint but real. You do not feel a hand on your back. No one shoves you toward the hills. Yet with each step the emptiness behind you offers no reason to turn around. No shelter. No anchor. Gravity works in a similar way. It does not need to push. It only needs a difference between where mass is and where mass is not. When astronomers first noticed that the local group is moving at hundreds of kilometers per second relative to the cosmic microwave background, they imagined a great attractor ahead of us, a single massive target drawing us in. Later, with better surveys and more careful maps, the picture grew richer and stranger. There is indeed a concentration of mass ahead, a tangled region of clusters and superclusters. But behind us lies a yawning underdensity that contributes just as much to our motion by its absence as the overdense knots contribute by their presence. This is the subtle power of the dipole repeller. It is a valley of gravity carved not by substance but by lack, a silence that shapes the song. One cosmologist once remarked that the universe is sculpted as much by its voids as by its walls. And the dipole repeller is a clear example of that quiet sculpting at work. Where there are clusters, galaxies fall together. Where there are voids, they slide away, finding paths along filaments like beads rolling down hidden threads. From a contemplative distance, there is something almost spiritual in this picture. We are not only drawn by what we desire or by what glows brightly ahead. We are also shaped by what is missing behind us, by the empty spaces that no longer hold us. Our galaxy, our cluster, our entire tiny archipelago of light is being released from the grip of that underdense region, set adrift toward a richer part of the cosmic web. Think of the cosmic microwave background as a still lake, the reference surface of the early universe, smooth, nearly uniform. On that lake, our local group is a small boat already in motion, not because we fired an engine, but because the lake itself was once stirred by the distribution of matter and voids. Galaxies all around us carry similar motions, their paths bending toward dense regions and away from vast hollows, each one a tracer of the invisible shapes of gravity. In technical language, the dipole repeller emerges from reconstructions of the velocity field, revealing a direction from which motion diverges rather than converges. To the meditative listener, that phrase can be translated into something more poetic. There is a place in the universe where galaxies seldom gather, a wide quiet where structure is thin and light is rare, and our entire neighborhood is drifting gently away from that silence, toward a busier crossroads of the cosmic web. When you close your eyes and imagine this, you might see our galaxy as a lantern bound to countless others by threads of dark matter, all of them moving in slow motion along invisible slopes. Ahead, dense intersections of those threads form clusters and superclusters. Behind, some strands thin out and vanish into emptiness. We are like a traveler walking from a sparse desert into a valley of rivers and forests. not because the desert is angry and pushes us away, but because there is little there to make us stay. Astrophysicists often say that structure in the universe grows from tiny primordial ripples, places where density was slightly higher or slightly lower than average in the early cosmos. Over billions of years, those ripples amplified, high spots gathering matter into halos and galaxies, low spots emptying out into voids. The dipole repeller is likely one of these low spots on a grand scale, an ancient underdensity whose influence has quietly guided our motion from the beginning. In a sense, then, our journey through space is not random. It is the unfolding of a pattern written into the fabric of the early universe. We are carried along by choices that were never ours, by initial conditions that predate every star and every planet we know. By the way matter and emptiness distributed themselves in the first moments after the Big Bang. To study the dipole repeller is to study that deep ancestry of motion, to trace our present drift back to a time when nothing solid yet existed. Some researchers like Netta Barkal have emphasized that mapping these flows is essential if we wish to weigh the universe, to understand not just where galaxies are, but how gravity moves them through time. The dipole repeller is a piece of that puzzle, a signpost that tells us where the density of matter drops and how that drop influences everything around it. When we include both the massive attractors ahead and the vast emptiness behind in our models, the strange dipole pattern of our motion suddenly makes sense. For a moment, imagine experiencing this not as data but as a feeling. You are floating in a dark sea, stars scattered like distant lanterns, your body weightless. Behind you, an endless darkness stretches with almost nothing in it. In front of you, there is a faint glow where many lights gather together. You do not feel pushed. You simply find that every gentle tug on your skin comes from ahead. Every whisper of gravity carries the same direction. Slowly, inevitably, you drift toward that collective glow, leaving the quiet behind. That is the story the dipole repeller tells, a story where nothing itself becomes an actor, where absence writes a line in the script of motion. It reminds us that in the universe, as in life, what is missing can be as powerful as what is present. The empty spaces in our histories, the gaps in our understanding, the silences between our questions, all of these shape the paths we follow. So, when we ask whether the universe can push galaxies, the answer is quietly subtle. There is no new force, no cosmic hand shoving us away, only the delicate interplay of density and emptiness, of attraction ahead and release behind. We are not being expelled from that void so much as we are being allowed to leave, guided by the gentle pull of richer structures that lie in front of us. As you let this image settle in your mind, you may notice your breath slowing to match the vast timescales involved. Billions of years in each inhalation and exhalation. Our galaxy moves only a small fraction of its own diameter in a human lifetime, yet over cosmic ages. The path traced by that motion is a graceful arc sculpted by voids and clusters alike. To fall asleep under such a sky is to remember that we are passengers in a universe that is still unfolding, still rearranging its matter and its emptiness in patterns too grand for any single mind to hold. In the end, the dipole repeller is not a villain and not a savior. It is a reminder, a quiet sign that even nothingness has a role to play in the dance of galaxies. And as we drift between the great attractors ahead and the great emptiness behind, we find ourselves in a position both humble and extraordinary. able to measure these flows, to map them, and to turn them into stories whispered at the edge of sleep. Who is really creating the pull that drags whole clusters of galaxies toward the Great Attractor, and how much of that gravity belongs to the dark matter we cannot see? We look out into the sky and we see stars glowing like scattered embers on a black ocean. We map galaxies and clusters. We trace their motion. And we discover something unsettling. The visible matter is not enough. The light is just the foam on the wave, not the deep water beneath. The true landscape of gravity is carved by something hidden, something that does not shine, yet holds entire superclusters in its silent grip. That is why when we speak of the Great Attractor, we are also whispering about dark matter, distribution, about the invisible skeleton that gives this giant gravitational ghost its shape. Imagine the cosmos as a vast forest at night, where you can only see the fireflies. You might think the fireflies define the forest, until you feel the trees, the ground, the roots pressing under your feet. Galaxies are the fireflies. Dark matter is the forest. We cannot see the branches, but we feel their presence in the way the fireflies drift and swirl. In the same way, astronomers do not see dark matter directly. They read its signature in the peculiar velocities of galaxies, in the way those galaxies refuse to move according to visible mass alone. When we talk about the Great Attractor, we are not talking about one brilliant object. We are talking about a region of space where gravity thickens like fog in a low valley, where the paths of thousands of galaxies bend in the same direction. Visible clusters like the Norma cluster and the long wall of galaxies around it are only the tip of the iceberg. Beneath them, wrapped around them, threading between them, is a halo of dark matter so vast that our words feel small when we try to describe it. As the astrophysicist Vera Rubin once said, "The universe is not made mostly of the stuff that makes up stars and people. Most of it is something else." Her careful work on galaxy rotation first made it impossible to ignore this invisible mass. And today the same idea stretches outward to the scale of the Great Attractor. To understand how much dark matter may live inside this gravitational giant, scientists play a quiet game of cosmic detective. They measure how fast galaxies are moving toward this region. They compare that speed with the amount of visible matter they can count. The numbers do not agree, just as they did not agree in the rotations of spiral galaxies. Something more is pulling, something heavier than all the stars and gas combined. Cosmologists estimate that across the universe, roughly 85% of the matter is dark. It would be strange if the Great Attractor were an exception, a cathedral of gravity built only from luminous bricks. Much more likely, its true mass is dominated by halos of dark matter stacked and braided together, shaping the overall pull while the bright galaxies simply trace out the bones. One can picture the Great Attractor as a deep basin carved into the fabric of space-time, a depression formed not by a single stone, but by countless grains of invisible sand. Each grain is a clump of dark matter, small or large, gathered by gravity over billions of years. As they accumulate, they turn a gentle slope into a steep valley, and galaxies, like marbles on a rubber sheet, begin to roll inward. Yet from our vantage point, we see only the marbles, never the hand that pressed the sheet. That hand is dark matter, and its fingerprints are the flows of galaxies we observe. Astrophysicist Jim Peebles once reflected that our universe is not only stranger than we imagine, It is structured in ways that make imagination itself stretch. Dark matter is central to that structure. Without it, the cosmic web would not have the same delicate yet robust pattern of filaments and nodes. Without it, galaxy clusters would fly apart instead of holding together. The Great Attractor seems to be one particularly dense knot in this web, an intersection where filaments of dark matter converge. When we travel through space in our thoughts, drifting with the Milky Way along its unseen path, we are really following these filaments, sinking slowly along gradients of invisible mass. And yet, for all its importance, dark matter remains humblingly mysterious. We call it matter, but we have never held a single particle of it in our instruments. We give it a name, but as the physicist Fritz Zwicky, who first inferred its presence, might remind us, a name is not an explanation. We invent candidate particles, imagine exotic symmetries, build detectors in deep mines and beneath mountains, all in the hope that one day a trace of this invisible majority will flicker in our data. Until then, the sky itself is our laboratory. The way galaxies fall, the way clusters bind, the way the Great Attractor pulls, all of it whispers the same message. There is more mass than meets the eye. Some researchers attempt to map the distribution of dark matter in and around the Great Attractor by reconstructing the flows of galaxies in 3 dimensions. They treat each galaxy like a leaf floating on a river, then rewind the current mathematically, asking what shape of riverbed could produce such a motion. In these reconstructions, the light of galaxies becomes a tracer, a dye traveling through an invisible fluid. The resulting maps suggest that the Great Attractor is embedded in a larger supercluster, that the pull we feel may be shared with even more distant overdensities. Through it all, dark matter forms a continuous skeleton, its density rising and falling like the contours of a silent landscape. Theoretical physicist Nima Arkani Hamed once remarked that our current picture of space-time might be only a crude approximation, that at a deeper level the universe may be woven from patterns we have not yet named. Dark matter could be part of that deeper pattern, not just an extra ingredient, sprinkled into an otherwise complete theory. When we ask how much of the Great Attractor is made of dark matter, we are really asking how deeply this unknown component is woven into the very definition of gravity and structure. If it makes up most of the mass there, and most evidence suggests that it does, then the visible galaxies are simply lanterns hung along an invisible architecture that existed first. Light arrived late, falling into wells sculpted long before stars were born. In the quiet of the night, when the noise of the day has faded and only the soft hum of your own thoughts remains, it is strangely calming to imagine this hidden scaffold, to know that beyond the thin film of starlight there is a deeper order, a slow and patient design written in gravity. The Great Attractor then becomes less a monster dragging us against our will, and more a reminder that we are part of something vaster than our senses can reveal. We are drifting along valleys in an unseen landscape, carried not only by the expansion of the universe, but by contours of dark matter carved over billions of years. So when we ask who truly creates the pull, the honest answer is that the visible matter plays only a supporting role. The stars and gas provide the glow, but the dark matter sets the stage. It likely supplies most of the mass of the Great Attractor, decides the depth of its gravitational well, and sculpts the pathways along which galaxies like ours must travel. We do not yet know what dark matter is, but we can already see what it does. It gathers. It binds. It guides. And as we float through space, rocked gently by the currents of this invisible ocean, we are left with a quiet thought. Perhaps the truest map of the universe is not drawn by light at all, but by the unseen hands that light is forced to obey. How can invisible islands of gravity and vast silent voids weave the entire architecture of the universe we live in? When we look out into deep space, we see scattered galaxies shining like lonely lanterns on a dark ocean. Yet underneath that simple view, there is a hidden pattern, a grand design that astronomers call the cosmic web structure. In this web, the true sculptors are the overdense regions and the underdense voids, the heavy knots and the empty hollows, pulling and releasing matter across billions of light years. An overdense region is a place where there is just a little more matter than average at the beginning. But gravity is patient. Over cosmic time, that small excess becomes a hill in the gravitational landscape, and everything nearby slowly slides toward it. The voids are the opposite. Regions that started just a little emptier than average. Yet as matter flows away into the hills and ridges around them, the voids grow even emptier, becoming vast, nearly weightless basins in which almost nothing remains. Step back far enough, and these hills and hollows link together into filaments, walls, and clusters. Threads of galaxies that look almost organic in computer simulations, like veins of light growing through a dark cosmic body. Clusters form where many filaments meet, giant crossroads of matter where thousands of galaxies orbit in a shared gravitational well. Walls are extended sheets of galaxies, bridges between clusters, sometimes spanning hundreds of millions of light years. And between them lie the voids, great black caverns of space whose quiet contributes just as much to the pattern as the busy, crowded hubs. What is astonishing is that this intricate tapestry grows from almost nothing, from tiny ripples in the early universe measured in the cosmic microwave background, differences in density of only 1 part in 100,000. Theoretical physicist Stephen Hawking once reflected that if those early ripples had been slightly smaller, galaxies and stars might never have formed at all. And if they had been larger, the universe might have collapsed into black holes too quickly for life to appear. So the very existence of the cosmic web structure is a delicate balance, tuned by the laws of gravity and the initial conditions of the Big Bang. To understand how the great attractors and other massive nodes shape this web, imagine the universe as a vast landscape of flowing water. But the water is made of galaxies. Wherever there is an overdense region, a supercluster or a great attractor, the flow bends toward it, like rivers curving toward a deep lake hidden beyond the horizon. Astronomers call the extra motion toward these regions peculiar velocity, because it is motion beyond the general expansion of space, a deviation from the smooth Hubble flow. This is where galaxy streams become our clues, our fingerprints of the unseen. By carefully measuring the direction and speed of thousands of galaxies, cosmologists can infer where the hidden masses sit, even if those masses are largely composed of dark matter that does not glow in any wavelength of light. As astrophysicist Vera Rubin helped reveal in her work on galaxy rotation, the visible stars are only the bright foam on top of a much deeper dark ocean. Most of the mass is invisible, yet it commands the motion of everything we see. In the same spirit, cosmologist J. Richard Bond has described our situation as living within a great cosmic web of dark matter, with gas and galaxies merely tracing out the densest strands. We do not see the web directly. We feel it through motion, through the subtle tug that bends the paths of galaxies away from what a simple expanding universe would predict. Each great attractor, each supercluster is a knot in that web, and each void is a place where the web has thinned almost to nothing. The balance between attraction and emptiness is more subtle than it first seems. Dense regions pull. Empty regions almost seem to push. Not by any new force, but because there is simply less gravity holding galaxies back inside them. As a result, a galaxy near the edge of a void will tend to drift away from the emptiness and toward the surrounding filaments and clusters, much as a ball on a rubber sheet rolls away from a shallow spot and into a deeper depression. When we place all of this on a map, the universe stops looking like a random scatter of lights and begins to resemble a living structure. Simulations such as those pioneered by Simon White and his collaborators reveal this with breathtaking clarity. Start with dark matter particles in a nearly uniform box. Let gravity act for billions of years, and filaments and clusters naturally appear. What we observe with telescopes aligns strikingly well with these predictions, confirming that the cosmic web structure is not an illusion but a real outcome of the underlying physics. There is something quietly meditative in this picture. Each galaxy, including our own, seems so self-contained when we look at its spiral arms or its glowing core. Yet on the largest scales, it is only a bead on a thread, part of a filament stretching from one gravitational hub to another. Our local group drifts toward a dense region, sometimes called a Great Attractor, while also being gently released from the pull of an immense, nearby void, pushed and pulled at once by the structure of the web around it. Cosmologist Netta Barkall has remarked that the distribution of clusters and voids is like a fingerprint of the universe, encoding the story of how matter has evolved since the earliest times. By studying how rich clusters gather at the intersections of filaments and how wide the voids grow between them, we read the history of cosmic expansion, the strength of dark matter, and the influence of dark energy stretching space itself. The web is therefore not only a structure but also a record, a fossil of the universe growing older and more complex with time. In a more personal sense, this knowledge gently shifts our perspective. We often imagine ourselves as tiny and isolated, a single species on a small planet in a modest galaxy, floating in a vast emptiness. Yet the cosmic web suggests that we are deeply connected. The Milky Way is woven into filaments of dark matter. Those filaments link us to clusters hundreds of millions of light-years away, and all of it arose from the same faint ripples in the primeval fireball. In the quiet of the night sky, this can become almost a form of meditation. Imagine tracing a line from our Sun to the center of the Milky Way, then outward along the filament that holds our galaxy, then further still to the next cluster and the next, until the mind can no longer picture the distances. Every step of that path is guided by the invisible architecture of overdensities and voids, by the same gravitational laws that shape the falling of an apple and the orbit of the moon. There is also an open-ended mystery that keeps scientists awake at night, even as this kind of story may gently lull listeners towards sleep. We still do not know exactly what dark matter is, only that it seems to form the scaffolding of the web. We still do not fully understand dark energy, the phenomenon causing the expansion of the universe to accelerate, slowly stretching the web and threatening to thin its filaments over unimaginable timescales. One day, far in the future, galaxies not gravitationally bound to us may drift so far away that their light will never reach our descendants, and the cosmic web will appear smaller and lonelier from their point of view. For now, however, we are living at a fortunate moment. We can still map large pieces of this structure, still trace the flows of galaxies toward great attractors and away from giant voids. Still test our theories with powerful surveys and supercomputer simulations. In doing so, we are not just cataloging distant objects. We are learning how the places of greatest attraction and greatest emptiness together compose the grand geometry of existence. So when we ask how the great attractors and the silent voids shape the universe, we are also asking a quieter, more intimate question. Where are we in this vast design? And what does it mean that our entire galaxy is just one bright knot on a thread of the cosmic web structure? The answer is not a final statement but a feeling, a mixture of humility and wonder, as if the universe itself were inviting us to trace its hidden lines with both our instruments and our imagination. Are we truly falling into the Great Attractor? Or are we only drifting along a silent current of gravity that began long before we were born? Imagine our galaxy not as a grand central home fixed in space, but as a small luminous boat on a dark cosmic ocean, carried by a tide it did not choose. The stars around us seem calm, the constellations familiar. Yet when astronomers measured our motion against the faint afterglow of the Big Bang, they found that the Milky Way is racing through space at hundreds of kilometers every second, more than 1 million miles every hour, as if some distant shore were calling us by name. This is where the mystery of galactic motion begins, because in a universe that is expanding in all directions, we would expect galaxies to drift apart almost smoothly, like dots on an inflating balloon. Yet our galaxy is not only riding that expansion, it carries an extra velocity, a peculiar motion, a subtle deviation that whispers of invisible structures shaping our path. As the cosmologist Jim Peebles once suggested, the universe is not a random scatter of islands, but a web of flows and patterns waiting to be mapped. When scientists traced the direction of our motion, they found that we, along with thousands of nearby galaxies, are streaming toward a region of space we cannot easily see, a place veiled behind the bright disk of our own galaxy. They called this region the Great Attractor, not because they understood it, but because they could feel its pull in the data. The name itself sounds almost mythic, like some ancient god of gravity sitting beyond the horizon. Yet the reality appears to be even stranger. The Great Attractor is not a single shining beacon, not a lone monstrous black hole waiting like a mouth of darkness. Instead, it seems to be a crowded intersection in the cosmic web, a knot of galaxy clusters, filaments, and probably oceans of dark matter, all woven together into a dense gravitational landscape. One can imagine it as a valley in the fabric of space, and we are like rivers of galaxies, quietly sliding down its slope. The astrophysicist Avi Loeb often reminds us that gravity leaves fingerprints not in light alone, but in the motion of everything that falls under its influence. We do not see the sculptor, only the chisel marks left in the sky. Yet even this picture is not complete, because as observers looked farther out, they discovered that the Great Attractor itself might be only a bend in a greater flow. Beyond it lurks the Shapley Supercluster, an enormous congregation of galaxies whose mass could rival or exceed the pull we first blamed on the Great Attractor. Like discovering that the river we thought ended at a lake actually continues toward a larger unseen sea. Our local group, the Milky Way, Andromeda, and their companions, may simply be passengers on a vast gravitational current stretching across hundreds of millions of light years. At the same time, the universe itself is expanding faster and faster under the influence of dark energy, that mysterious component that makes up most of the cosmic budget. Stephen Hawking once remarked that understanding dark energy is one of the greatest challenges in modern physics, because it seems to push space apart even as gravity tries to pull matter together. This tension creates a quiet drama beneath every starry night, a cosmic tug-of-war, where neither side fully wins in the present moment. Here is the subtle beauty of our situation. We are moving toward something, yet we may never arrive. Dark energy ensures that on the very largest scales, structures that are not already tightly bound will slip away from one another, like lanterns drifting apart on an ever-widening river. So when we ask whether we are falling into the Great Attractor, we must admit a quiet possibility, that we are instead sliding through its region of influence, feeling the memory of its pull without ever reaching a final shore. In the distant future, those flows themselves may be frozen by accelerated expansion, as if the river slowly turned to glass. In this sense, our journey has no simple destination. There is no fixed point in space where the story ends, no cosmic harbor where the Milky Way will finally rest. The theoretical physicist Nima Arkani Hamed has famously said that space-time as we picture it may be doomed, that our familiar notions of distance and motion are only emergent shadows of a deeper quantum reality. If that is so, then even the idea of falling into a specific place might be less fundamental than the pattern of relationships that tie all things together. Still, something very real is being measured. The cosmic microwave background provides a reference frame as ancient as the universe itself, and against this gentle glow our motion stands out as a clear dipole, a warm side and a cool side, like the sensation of wind on your face telling you that you are moving even when your eyes are closed. We know the direction of our travel. We can estimate its speed. But the deeper question remains. What does it mean to move through a universe where every reference point is also in motion? The more astronomers map these flows, the more the cosmic web reveals itself as a system of gentle guidance rather than hard boundaries. Galaxies stream along filaments, gather in clusters, and drift away from vast, under-dense voids that act almost like invisible hills, pushing them toward richer regions. Some researchers describe a phenomenon called the dipole repeller, a massive cosmic void behind us that contributes to our motion by its very emptiness. Not by pulling, but by failing to hold us back. It is a quiet reminder that absence can shape reality as deeply as presence. Within this living landscape, the phrase galactic motion becomes more than a dry technical term. It is the story of how matter flows through the universe, how gravity and dark energy, structure and emptiness, collaborate to choreograph the paths of billions of suns. Carl Sagan once said that we are like butterflies who flutter for a day and think it is forever. And when we consider the slow migration of galaxies over billions of years, his words feel achingly precise. Our entire civilization is a brief shimmer on the surface of a galaxy that is itself gliding along a path we only just learned to notice. From a more human perspective, there is something strangely comforting in this idea. We are not standing still, yet we are not lost. We belong to a flow so large that our worries and boundaries shrink to their proper scale, like ripples on a river that has been running since the dawn of time. To lie back under the night sky, aware that every star is a companion on this shared journey, is to feel both small and deeply connected. The universe is not merely a backdrop for our lives. It is the moving ocean that carries us along. So, are we falling into the Great Attractor, or just drifting in a gravitational current that stretches far beyond it? Perhaps the truest answer is that we are doing both and neither. We are responding to the shape of the cosmic web in this moment, even as that web slowly changes under the influence of dark energy. The path of our galaxy is one line in a larger tapestry, a pattern still unfolding, where attraction and expansion weave together a story too vast to finish in a single lifetime. In the quiet between heartbeats, when you look up at the stars and feel a faint sense of motion you cannot name, you are touching that story. You are a small part of a galaxy that is itself a small part of a supercluster, sliding through a field of invisible forces toward an undefined future. And perhaps, as we fall and drift and circle through this immense design, the real destination is not a point in space, but a deeper understanding of the universe that carries us. Why would mapping the hidden gravitational giants of the universe change everything we think we know about reality? We talk about cosmology as if it were a neat collection of equations and images from telescopes. Yet beneath all of that there is a quieter quest unfolding. A quest to understand why our galaxy and thousands of others are not just drifting away with the expansion of space, but falling together along invisible slopes of gravity. To trace those slopes is to practice something we might call cosmology mapping, the art of drawing a map of a universe we cannot touch, guided only by faint light and subtle motion. When astronomers first noticed that the Milky Way was moving in a particular direction with a peculiar velocity that could not be explained by expansion alone, it was as if the floor under our familiar cosmic model shifted a little. We were no longer mere observers sitting in a quiet corner of space. We were passengers in a current. Brent Tully and his colleagues began to collect these velocities and distances, measuring how galaxies flowed through space rather than simply where they were fixed on the sky. And a pattern emerged, a great streaming motion toward what we now call the Great Attractor. Like leaves on a slow river, galaxies were all slanting in the same direction, hinting that somewhere out there was a heavy hand on the fabric of space. Why does this matter to modern cosmology? Because every deviation from smooth expansion is a message about unseen mass. Every peculiar velocity is a whisper from dark matter. Vera Rubin once remarked that what you see in a galaxy is only the tip of the iceberg. And the rotation curves she studied showed that most of the iceberg is invisible. In the same spirit, these giant flows of galaxies show us that the universe itself is laced with enormous icebergs of mass that do not shine. By measuring how galaxies move toward regions like the Great Attractor or the Shapley Supercluster, cosmologists turn motion into a kind of sonar, bouncing questions off the darkness and listening carefully to how the cosmos responds. To understand why this is the only way to map dark matter on the largest scales. Imagine standing in a foggy valley at night. You cannot see the mountains or the cliffs, but you can roll a ball across the ground and watch where it speeds up or curves away. From that motion you infer the hidden landscape. Galaxies are those rolling balls, and the fog is the limitation of our direct vision. We see stars and gas, but not the scaffolding of dark matter that shapes them. Jim Peebles has said in many ways that large-scale structure is the fossil imprint of the early universe. The way matter clumps today is a stretched memory of quantum ripples from the very beginning. If we wish to read that fossil record properly, we must know not only where the galaxies are, but where they are going and why. Flows toward attractors and away from vast voids like the dipole repeller reveal the bones of the cosmic web. the filaments and nodes where dark matter gathers, and the bubbles where it is scarce. This web is not decorative background. It is the true stage on which cosmic history plays out. Galaxies form where the web is thick. Clusters grow at its intersections. Superclusters stretch along its strongest threads. If we fail to map these gravitational highways, we misunderstand not only where matter is now, but how it learned to arrange itself from the first moments after the Big Bang. There is also a humbler reason this matters. It tells us where we truly are, not just in coordinates and numbers, but in relationship to everything else. We like to imagine the Milky Way as a kind of quiet island, floating still in a dark sea. Yet in reality, our home galaxy orbits within the local group. That group drifts toward the Virgo cluster. Virgo and its neighbors flow into the basin of the Great Attractor. And all of this is woven into the immense supercluster called Laniakea. To know these flows is to realize that we are not stationary at all. We are part of a slow, graceful migration across hundreds of millions of light years. Sean Carroll once noted that in cosmology we are trying to understand not only how the universe works, but what kind of story it is telling. Mapping these attractors and voids reveals that the story is not a static picture but a long journey, a pilgrimage through a landscape of gravity. From a technical viewpoint, this work also tests the very fabric of our theories. If general relativity is our language for gravity, then the large-scale flows of galaxies are the longest sentences ever written in that language. They stretch across hundreds of millions of light years. And if the grammar were wrong, we would see it in how those sentences bend and twist. By comparing observed flows to simulations based on dark matter and dark energy, cosmologists ask a sharp question. Does our model of the universe produce the same rivers and eddies of motion that we actually measure? If the answer is yes, our confidence grows that our invisible components and our equations are roughly right. If the answer is no, then somewhere in the darkness a new idea is waiting to be born. Nima Arkani Hamed has provocatively said that space-time itself may be doomed, meaning that the smooth continuum we use in our theories might only be an approximation, the way water seems continuous, though it is made of molecules. Mapping cosmic motions with high precision may be one of the ways we eventually detect where that approximation breaks down. Yet beyond the mathematics there is a quieter human dimension. When we look at a map of Laniakea and see the Milky Way as one tiny thread in a vast river of galaxies flowing toward a distant gravitational basin, something shifts in us. The old picture of the isolated galaxy gives way to a sense of belonging to a structure so grand that it defies ordinary language. We are not simply in a galaxy. We are in a current. And the current itself is part of a larger tidal pattern shaped by dark matter and expansion and the ghosts of early quantum fluctuations. To many listeners trying to fall asleep under the gentle hum of a late-night documentary, this can feel almost like a cosmic lullaby. The idea that we are carried, that there is a pattern underneath the apparent randomness, that our motion is not frantic, but part of a slow choreography measured in billions of years. Understanding the Great Attractors also reframes the way we think about fate, not in the mystical sense, but in the dynamical sense. The future of our cosmic neighborhood is written in these flows. Will the local group eventually merge into a larger structure or remain a lonely island as dark energy stretches the universe ever faster? How many collisions and mergers lie along our trajectory through Laniakea? When we simulate these paths forward in time, we glimpse a future in which only the nearest structures remain visible. Distant galaxies pulled beyond our horizon by accelerated expansion. In that far epoch, the memory of today's cosmic web may survive only in the fossil motions already imprinted in local orbits. What we map now becomes a kind of time capsule, a record of the wider universe that future civilizations may no longer be able to observe directly. Every time we refine a catalogue of galaxy velocities, every time a new survey peers through the dusty plain of the Milky Way to find hidden clusters feeding the pull of the Great Attractor, we are doing more than filling in a chart. We are learning the deep context of our existence. We are discovering that our sky is not a random scattering of lights, but the visible trace of an underlying structure that began as tiny ripples in the early universe and grew under gravity into the grand design we now inhabit. So when we ask why, understanding these great gravitational attractors matters to modern cosmology, the answer unfolds on many levels at once. It matters because it is our best way to map dark matter across unimaginable distances, to turn the silent pull on galaxies into a picture of the unseen. It matters because it explains the flows that shape the cosmic web, the filaments and nodes where galaxies gather and evolve. It matters because it tells us where we truly stand in that web, not at the center of anything, but as part of a vast and intricate network of motion and relation. And it matters because in tracing these currents, we glimpse both our past and our future, from the first seeds of structure to the long dim era when only local galaxies remain. In the quiet of the night, as you listen to the slow story of galaxies drifting along invisible rivers of gravity, you might feel a gentle shift in perspective, a sense that to be human is also to be a node in this great map. A brief awareness arising inside a galaxy that is itself gliding through the arms of Laniakea. Perhaps that is the most intimate reason cosmology mapping matters, not only because it tells us what the universe is made of, but because it helps us remember where we are in it, and invites us to drift a little more calmly through our own small span of cosmic time.